Dear students, I think when we reach this forced oscillation, we will end up with this final expression as shown in the equation 29. And here I just wanted you to play around this function and see. So I just kept this omega naught equal to, sorry, say 10. C was given the value. So I just arbitrarily kept some values. For example, I just gave this, don't worry about this one, I just try to plot it over from cloud to give the feel of this resultant function of this two sine function which has been overlapping, and one we have got this forced oscillation part coming in, and the second one, the first one is the exponential decay part of the amplitude. And here I randomly choose some values for omega which is 10, for C I chose the value as 2, and it was plot over a range for x values from 0 to 20, and the p values you can tune it from 0 to 20. So the thing is that you should see the maximum amplitude coming in when p is equal to 10. So that is what I'm trying to show you. So when I slowly increase p, so if there is, so in this particular case when there is no forced oscillation, the oscillator dies off very quickly. And in process of p, if you increase p, you can see that the forced oscillation is trying to make this thing oscillatory, and when it is p for the value so and so. And you can see that when it reaches 10, which is omega naught value for this particular system, the amplitude will be maximum. So now it is at 6, you can see the amplitude is increased slightly. For 8, it is again increased, it's periodic, perfect. And at 8, you will have the maximum resonance, the amplitude will be the maximum. So you see that at this range we got the maximum amplitude so far. So if you make it increment to again next value, the amplitude value will drop from that value. So you can see that the p value will make sure that the initial, if you increase the tune the p value, slowly we will see that the amplitude is increasing, but at this point we will reach that we have got maximum, and beyond that we are going to get back the same old story of this thing. So that is being shown in this plot. So this idea that the amplitude we are going to get the maximum. So here we have plotted only the first part of this forced oscillation part where the A term is going to be high. So we have just plotted this f0 by root of omega naught square minus b square whole square plus 4c square p square. That term is A, and that is being shown here. But I am trying to, what I showed in the Wolfram cloud is basically this expression 29 together, considering few examples. To one thing to be noted here in this, whatever I said was that we are not seeing resonance exactly at p equal to omega naught, but in fact we are seeing resonance when p takes the value root of omega naught square minus 2c square. And the thing is that value, if so, around 9.82 or 84 we have this maximum value, you can see. But because since our c was very small, p was almost equal to omega naught, therefore we saw that resonance around omega naught. But usually if c is very small, the resonance happens almost near omega 0. That correction I forgot to mention earlier. So here I'm just showing the peak, the top regions, the amplitude was around 1. So when the p was 9.2, you can see this value is very close to 1. So omega 0 is 10, and using the formula for p, the resonance frequency point, it is around 9.6. So at 9.6 we should see the increase. So when this amplitude is increasing, you can see at 9.4, 9.6, it is again increased, right? So I'm asking you to concentrate on this region where this the peak points are hitting. So if beyond that, it is going to again decrease. So if I just so this is what we were saying all the time, that the resonance happens at the point where it is very close to omega naught, but exactly given by the formula root of omega naught square minus c square. Okay, so that's what I wanted to say. So it is replotted this one. So this is exactly the range from -5 to 5. Okay.